Alright, today we're going to talk about changes of states, and this is in states like Alabama, Mississippi, Pennsylvania, and Canada. Well, Canada, 51st state. This is changes of state of matter. So, states of matter. There are three states of matter: solid, liquid, and gas. You can also chunk plasma in there, but we're not going to talk about plasma. The state of matter of a substance can be changed through melting and boiling. If you didn't know that, then you've never had a glass of iced tea or ice in anything. That ice melts. So matter can change from one state to another when thermal energy is released or absorbed. So specific heat comes into play a lot with changing of states because we're either adding energy to a system or releasing it in order to change the state of matter. And that's called change of state. So when something melts, it takes in energy to change from a solid to a liquid. So to go from solid to a liquid, you have to take in energy. So all these red arrows are increasing energy, and the blue are decreasing energy. So just like when something melts, you need to change, or you need to add thermal energy to get that liquid to go to a gas. To boil it, you also need to add thermal energy. And the opposite is true. Take away energy from a gas, it condenses. And when you take away energy from a liquid, it freezes. So this figure below shows you what's going on with the temperature and energy as something changes state. So anytime that there is a horizontal line on the graph, that means that's where it changes state at. So we can see for water, temperature in Kelvin, 273 degrees Kelvin, which is 0 degrees Celsius, the point at which water freezes and melts. We can see it takes an awful lot of energy just to get that water to freeze. Water to melt. Because it jumps from 61.7 joules, and you have to add all the way up to 395.7 joules to get it to freeze. Now this entire time, this water is like in between, freezing and between liquid and solid. Anytime you see a sloped curve, that's during that change of state. That's while it's in one state or another. It's like right here, it's all ice. Here it's all water, and up here it's all steam. You see, it takes even more energy to boil something because it jumps from 813.7 joules to 3,073 joules to change water into steam. That's a pretty big joule difference. So at some point, the added thermal energy causes the particles to move rapidly enough that their motion overcomes the forces holding the particles together in a fixed location. So we keep adding energy till those bonds break. So in ice, the water molecules are really densely packed, but we keep adding heat to it, and the particles start moving fast and fast and fast, and they break apart, and they become water molecules. So the particles are still touching each other, but they have more freedom of movement. And eventually, the particles become free enough to slide past each other. So this is what happens in a liquid. Like the water molecules, they're still touching, but they can slide freely past one another. All right, now we're going to talk about its melting points. So at this point, the substance has changed from a solid to a liquid. Makes sense? We know stuff melts. It goes from being hard to, a liquid. The temperature at which this change occurs is the melting point of the substance. So for water, 273 K. For other things, it could be higher or lower, like carbon dioxide, dry ice. It's a much, much lower melting point. So when a substance is melting, all of the added thermal energy goes to overcome the forces holding the particles together in that solid state. And that's why we had those horizontal lines on that graph, because all that energy is just going into melting it. It's not raising the temperature, it's making those molecules move faster and faster. So none of the added thermal energy increases the kinetic energy of the particles, rather the temperature does not increase. So hence the horizontal lines. So this ice cube, while it's melting, like the entire time while this thing is ice, its temperature is 273 K or 0 C. The entire time while it's solid. Now there's a liquid over here, it's already melted, down obviously going to have a different temperature. So as I said, the horizontal lines, this is where that ice is melting. It's still ice, it's still 273 K, but until it reaches 395.7 joules added, it's not all going to be water. So because the kinetic energy of the particles does not increase, the temperature does not increase. So it stays at 273 until that ice turns to water. Now, similarly for the boiling point, it's pretty much the same exact spiel as the melting point, but we just need a lot more energy. So once the solid's completely melted, there are no more forces holding it together in the solid state. So adding more thermal energy increases the motion, which in turn increases the temperature. That liquid's going to rise in temp. So we can see this between here and here. Temperature goes up by 100 degrees, by 100 Kelvin. All that energy we're putting in, we put an extra, about 400, a little over 400 joules in. That just goes into heating up that water. So as the temperature increases further, some particles in the liquid acquire enough energy to break free from the other particles. So at a specific temperature known as the boiling point, further addition of energy causes the substance to undergo another change of state. And all the added thermal energy converts the substance from liquid to the gas. So again, while it's going from liquid to gas, it's always that same temperature. It's always that 373 K. So as in melting, the temperature does not rise while the liquid boils. It stays at that 373 K. So while you're boiling pasta on the stove, it doesn't matter how much heat, how high that flame is, as long as that water is boiling, it's always the same temperature. You could have that sucker jacked up on high, and it's still going to be 373 degrees as long as that water is boiling. So just like the ice staying same temperature, all this water in this pot, if this is boiling, it's all going to be 373 K. Now, steam is a lot harder. That's why you can get burned a lot easier with steam than you can with water. This is greater than 373 K up here. So back to our graph, where we have between D and E is, wow, the water is changing into steam. And a little jagged line here means we cut out a big chunk of that because, this is about 2,200 joules we had to add in here. We extended it out to be, way off the screen. So if the material is entirely converted to gas and the added thermal energy increases the motion of the particles and the temperature rises. So that steam just gets hotter and hotter and hotter if you keep adding temperature to it, adding heat to it. So above point E, steam is heated to temperatures greater than 370 degrees. That's why, you want to stay away from the steam. Steam can hurt you a lot faster than boiling water. This also brings us to something called the heat of fusion. Heat of fusion is the amount of energy needed to melt 1 kilogram of a substance. So the added energy causes a change in state, but not in temperature, which we already said. So the horizontal distance from figure in this picture from point B to C is the heat of fusion. So this whole distance in here, this change in heat, that's the heat of fusion. And similarly, at the other end of that chart, we have the heat of vaporization. So at normal ATM, water boils at 373 K. So the thermal energy needed to vaporize 1 kilogram of water is called the heat of vaporization. For water, the heat of vaporization is 2.26 joules per kilogram. So we need 2.26 joules added to 1 kilogram of water to completely vaporize it. So the distance from D to E here represents that heat of vaporization. Take 3,073 and subtract 813.7. We're going to get roughly 2.26 joules per kilogram if we do a little bit of conversion. Right now this is in like grams, so you got to do thousands it. So every material has its own specific heat of vaporization. Between points A and B on here, there's a definite slope because we're increasing the temperature. And this slope represents specific heat of ice. So we find the slope of this guy, we find the specific heat of ice. And between points C and D, we find the slope of this guy, we're going to get the specific heat of water. And similarly, from E on, specific heat of steam. So note that the slope for water is less than those of both ice and steam. This is because water has a greater specific heat than ice and steam. So we can have a very simple equation for this heat of vaporization. So the heat, the Q, required to melt a solid of mass represented by M is given by the following equation. Q, heat, equals mass times that heat of fusion. Pretty simple equation. So the heat required to melt a solid is equal to the mass of the solid times the heat of fusion of the solid. Duh. It's M times H is. Same thing with the heat of vaporization. Instead of HF, we have HV. And if you don't know, multiplication means there's a little explanation for you. So when a liquid freezes, an amount of heat, Q equals negative M heat of fusion must be removed from the liquid to turn it into a solid. So this negative means that heat is going out of the system. We're going to have a negative Q. Anytime there's a negative Q, we're taking heat from the system. Positive Q, we're adding heat. See, negative sign indicates the heat transferred from sample to the outside world. In the same way, when water vapor condenses to a liquid, we're also going to have a negative heat. But this time, instead of HF, it's HV. Here are some common examples in joules per kilogram, depending on what values I give in problems or the book gives in problems. You might have to convert something like kilojoules or grams, so on and so forth. But these are basic ones. So you notice gold has a really high, actually no, what's the biggest one on here? It's the 5s. So water is actually the biggest heat of fusion. 6s, 5, 8, and methanol has a really high heat of vaporization. Alright, just a quick example problem. Suppose you're camping in the mountains. You need to melt 1.5 kilograms of snow at 0 degrees Celsius and heat it to 70 degrees Celsius to make hot cocoa. How much heat will be needed? So first, sketch a little picture. We're going to take 1.5 kilograms of snow, turn it into water. You can also add on here the transfer of heat as the temperature of the water increases. So Q goes into the snow. As that snow is melting, you've got to have the heat of vapor or heat of fusion going on here to turn it into water. Identify the knowns and unknowns. We know the mass of the snow. We know the initial temperature. We know the specific heat of water. Snow is just frozen water. We know the heat of fusion for water. We know how much water we're going to get out of it. And we know the final temperature we want to reach. Unknowns, we don't know the Q to melt the ice, the Q to heat the liquid, or the Q total. So we start over here at 1.5 kilograms of snow, and we end up with 0.5 kgs of water. That's because there's a lot of gases and stuff trapped in the snow too, released. Alright, so the heat needed to melt the ice, pretty easy. Yeah, 1.5 kilograms of ice, heat of fusion of water is 3.34 times 10 to the 5th. Multiply those two guys together, and you get 5.01 times 10 to the 5 joules. And oftentimes it's easier to convert this up to kilojoules, so that's 501 kilojoules. So now we got to calculate the temperature change. It goes from 70 to, or sorry, it goes from 0 to 70. It should be final minus initial there. Be final minus initial, typo. So it's 70 minus 0, it's a change of 70. Now we got to use our good old Q equals MC delta T. We're talking about heating the liquid. So we take our mass of our melted snow here, our specific heat of water while it's liquid, and the change in temperature. Plug it in, and you get 4.93 times 10 to the 5th joules, which we change it to kilojoules, 439 kilojoules. total heat needed, you just add the two heats together. 5.01, or 501 plus 439, you get 940 kilojoules. So are the units correct? They're in joules, makes sense. Does it make sense? Does the sign make sense? Yes, Q is positive because we're adding heat to the system to melt it and then to heat it. Is the magnitude realistic? Pretty much. That's it, thank you.